so we're going into chapter 11 today, radicals and geometry connections. So before we do, I want to do a quick kind of little thought about where we've come so far this year. And so the first kind of function that we graphed this year looked like, that's a really bad rendition, but looks like that. What is that called? Linear. And a linear function, give me our favorite form. Ready? Y equals mx plus b. And so what is the exponent value for the input here? 1. Very good. What's the input letter? The independent variable. X is your input. That's what changes. It's independent because you can put what you want in there. M is a given. What is M? Good. And B is y-intercept. Good. Okay, so that was our very first type of function. The second type of function was this type of function. And that is? Good, exponential. Right? And so what is the basic form or the model exponential function? Y equals AB to X. Very good. And so the input now, the independent variable is what? It's the exponent, right? That's what makes it an exponential function. Okay? And then the next type of function we worked with was this, which is? Quadratic. Quadratic. And so the parent quadratic, or the standard form, y equals?
ax squared plus
bx plus c. Good. And so the input, the independent variable has what exponent now? It's squared, which is why I said I would love to have seen it called squaredratic or something, but it's quadratic. So too bad it's not squaredratic. So today we're getting into this type of a function, radical. So what would you expect to see in the function? Y equals
a and x.
Square root of x. That's it. Square root of x. So we're going to be able to fill in this. We're going to be able to kind of show a model because we're going to graph this today. Okay, the square root of x. That's actually the parent function. And who can give me the parent linear function? What's the most basic linear function? Y equals y equals x, right? What's the slope of that function?
1.
The slope is 1. What's the y-intercept? 0. So we could call this direct variation too. Good. And so who knows the parent function for exponential? What's the smallest b you can have? That's an integer, let's say. 1 would make it linear because 1 to anything is just 1, right? So 2 is the most basic, 2 to the x. Okay, and how about quadratic? The most basic, the parent quadratic, y equals, very good, x squared. So we could throw out all that other stuff, and that will give you the basic parabola with a vertex at 0, 0, and it's just pointed upward, right? And so this is the parent radical function, and that's what we're getting into today. So just a quick review. Of some terms. If we have a radical expression, what will we see? Kyle, what will we see? Kyle, if you have a radical expression, what will we see? What is this? Yeah, a radical, right? Now, a radical can represent other roots, but when it's written in this form, it's a square root. We don't see the little 2 out here. There's an invisible 2 out here. There are cubed roots, and we could take the 4th root, and so on. And if you were asked to take a different root, you'd see a little number out here. Okay, like an exponent, but out here outside the radical. A radical function then has a radical expression in it. Just it has your independent and dependent variables with a radical in it, as we were just saying. But today, and in this chapter, we're just going to focus on square root functions, which are radical functions. Just taking square roots. So we're going to have the parent square root function highlighted in your notes so that we can draw all comparisons to it. So this has not been completed. We're going to do it together. The parent square root function is what you stated, y equals the square root of the input, the independent variable. So y depends on, it's the dependent variable, depends on what you stick in for x, right? Now, in most cases with linear, quadratic, exponential functions, we could input anything, right? But we're limited because of this radical. What may we not put in that radical, John? Negatives, because if you do, you don't get a real number out. We could get out an imaginary, a complex number, but not a real number. So we're going to be starting with the smallest possible number here. What would the smallest number be that we could put in that and get a value out? Something smaller than 2. Something smaller than 1. 0, right? 0. Good. So the very smallest value for x, whoops, is 0. I think I've been bumped. Okay, so the smallest x, smallest input value is 0. So then can we go, well, since it's the smallest, we have to go greater than that number, right? So we're identifying the domain when we're doing this. The domain are the inputs, the independent variables, x. X's need to be greater than, or they could be equal to 0. And then we'll figure out the range after we input these things. But before we go to the range, let's continue to look at what we can input. You can input anything greater than 0, but what are the easiest numbers to input into a radical?
Squares.
Perfect square numbers, right? So what's the next perfect square?
4.
Bigger than 0? 1, right? Square root of 1? And then we have 4, right? And then what's the next perfect square? 9. Good. Okay, so who can give me the range that we have in this case with these values? What is the square root of 0? Ellie? Square root of 1? Square root of 4? And the square root of 9? 3. Good. Okay, so we just simply plot these, and we'll see what the parent function looks like. This has, each of these units represents 1 on mine, right? And we start at 0, 0, 1, 1, 4, 2, 9, 3. So the y values are going to increase, but you can see it's looking flatter as we increase the domain, right? It's looking flatter, kind of like an exponential would often approach a certain, like, axis, right? And yet get closer and closer, but never touch it. So we have this thing that's getting flatter, flatter, but it will increase ever so slightly all the way out through to infinity and beyond, right? Okay.
Was it just like...
Right, so we would not draw an arrow on the left side because it has that starting point. We cannot go to the left, right? We can't take the root of a negative, the square root of a negative, and find a real value. It would be an imaginary or something. So we don't graph imaginary things. This is the real truth. So it's almost like a ray, isn't it? But a ray would be straight, like a line. This has got a little curve to it. So it's a little bump. So if we were to go back to where we were just kind of highlighting what we've done this year, we've now done we're doing a curve that kind of could look like this, right? Which kind of reminds us of the exponential, but look, at exponential goes both ways, right? It's not limited. Now, in some of these graphs this year, we have had a starting point because it was a real world thing, right? Like we were driving and we didn't go a negative distance, but we talked about how you could imagine going a negative distance using a linear equation or something. Okay, so let's do it. We're going to graph 2 together, and then you have your assignment. The first is a little different than the parent function. We're multiplying by 1/2. So what do you think will happen before we even do this, when we multiply by 1/2? Based on what we've done with other functions, what do you think might happen? What type of transformation could multiplying by 1/2 do? Vertical stretch or a vertical shrink? I mean, this is 1/2. What if it was 5 instead? Different effect probably, right? Who thinks this might be a vertical stretch? Who thinks it might be a shrink? Yeah, we have a few more thinking it might be a shrink. So we're going to do what we just did. We're going to make a table. And we're going to compare it to the parent. So the parent function is something that we can just put in by saying square root of 0 is 0, square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. We just did that table. So that's our parent. Y equals square root of x. Let's make a table. Let's make a vertical table this time. We should be able to use different types, right? And again, we're taking the square root of x, so we like to use maybe those same values, right? Because they're easy to take the square root of. 0, 1, 4, and 9. The only difference is, after we take the square root, we're going to multiply it by 1/2. So go ahead and find those values and come back. So there we have the values that you get when you plug this domain in. And there is kind of a pattern popping out. Somebody in the last class thought this looked like what? What kind of pattern does it remind you of? Linear, because you're doing a constant addition. See that? But why is this not linear? What in the table shows you it's not linear? Hey.
Because the x is like not
Right, we're not increasing by 1 or by some constant 2. Look at this. This is plus 1, this is plus 3, this is plus 5. This is not a constant increase in that domain, so it's not linear. But it is showing this neat pattern. And so let's go and graph these. 0, 0, 1 at 1/2, 4 at 1, and 9 at 1.5. Okay, so what is the transformation, Madeline? It's a what? We're looking at how the red is different from the black, and so it's a vertical shrink, actually. It's going away from the y-axis. It's like falling away, so vertical shrink. Okay, and then the domain are the x values, and who can describe that? Connie. The domain and range don't look different, but the graph looks different, doesn't it? Because it's shrunk. But the values that you may put in still start at 0, and the values that are coming out still start at 0. As we do other things to this function, I mean, we could add stuff out here, we could add stuff in here, we could do a negative over here. You know, we're going to see different domains and ranges, okay? And then the last one today, for your notes, negative 1.5 times your square root of x. So does anybody want to share what you think might happen now to the parent, Hank? Good, so we have some people thinking that this is a number greater than 1, right? The absolute value. So it might stretch it, and the negative might reflect it. We just said the number in front of this radical is really 1, right? That invisible 1. So this number is, the absolute value is greater than that. So probably a stretch. So we make a table. And because this radical has just the x in it, again, we are limited to starting with 0, right? 0, 1, 4, 9. And when we plug in 0, what do we get out, Jack? And when we plug in 1? And when we plug in 4, we end up with what? 2 times negative 1.5. 2 times, imagine that's 3 over 2, right? So negative 3, good. And then when you plug in 9, you get a 3, right? But 3 times 3 halves, 3 times 3 halves is negative 4.5. So we do see this increase, or this decrease of 1.5 in the y values. Okay? So we plug in these points. I'm going to pause this. Good, so there's what we have. If we compare that to the parent function, which would be here, what is the transformation? Again, we can see it really clearly. It's what you were thinking, right?
It's a stretch and a reflection.
It's a vertical stretch, good. And it's a reflection. And let's talk about the domain and range. Good, so we have x values still greater than or equal to 0, but the y values are now all less than. They'll never be greater than 0. Very good. And your assignment is here. You'll need graph paper.